Hi everyone. So let's work in this example. It is about conservation of angular momentum, one of your favorite. This one says, a thin uniform cylindrical turntable of radius 2.9 meters and mass 17 kilograms rotates in a horizontal plane with an initial angular speed of 11 radians per second. The turntable bearing is frictionless. A clump of clay of mass 4 kilograms is dropped onto the turntable and sticks at a point 0.9 meters from the point of rotation. That would be the center. Treat the clay as a point mass. Find the angular speed of the clay and turntable. Round to the nearest hundredth. And it says video because I'm recording exactly that video. So I have a link here on your review. Okay, so there's a lot of information packed in here. So basically we have a turntable. You can think of it as a disc, right? And then something drops and sticks to the, you can think of it as a record player, more or less, okay? The first thing I want to do is we have to specify subscripts for both objects which are part of this problem. The first one will be the thin uniform turntable, and the next one will be the clay. Okay, so just for convenience, I will label anything having to do with the cylinder. I know it's like a disc. I'm going to write on this side, on the right side. So cylinder or disc, right, will be 1. And then anything having to do with the clay, which is a point mass, will be having a 2. Okay? If this doesn't make sense yet, don't worry. Now let's write down what we have. So we start with the radius of the cylindrical turntable or the cylinder. So we'll say, let's write down given. So we have the radius, so we'll call it R1, right? Because that is for the disk. That is equal to 2.9 meters. And then we have its mass, still with the disk. So that'll be M1 is equal to 17 kilograms. Next, now that we're told that it has an angular speed of 11 radians per second. That is the Greek letter omega, kind of like that, and that is omega initial, okay? This is a 1, and this is initial. That is 11 radians per second. Let's try that S again. There you go. Now we have information about the clay. So we have a mass, that'll be mass 2 of 4 kilograms. And then it sticks at a point of 0.91 meters from the center. So that is another radius. So R2, 0.91 meters. And we have to find the angular velocity or angular speed of both the clay and the cylinder or turntable. So that is simply the final velocity, well, angular speed, right? Because they're going to be rotating at the same rate. This omega final applies for both. Okay, as I said, this is a problem about conservation of angular momentum. So what it says is the angular momentum of the system before will equal the angular momentum after. Now, if you think about what's happening, the before is just the turntable rotating. That's it, right? So just the angular momentum of the cylinder. And then we have the combination of the angular momenta of the cylinder plus the clay. Okay. And in case you forgot what angular momentum is, we use letter L. And just the general formula is I omega, where I is moment of inertia. Okay? And so the way we can set this up is angular momentum initial will be equal to angular momentum final. The issue is here we're not separating, right, which angular momentum we're talking about. So let's do that now. So before, we only have the angular momentum of the cylinder. So we'll say L1 initial will be equal to the sum of L1 final, that is the angular momentum of the cylinder, plus L2 final, that is the angular momentum of the point mass. And I think it's a good time for us to define the moment of inertia. Don't forget that those values, you can find them on your formula sheet. So let's start with the cylinder. So the angular momentum of the cylinder, so that'll be I1. Since we have a cylinder or disk, we're going to be having 1/2. Now the formula says mr squared, but we know that this is m1 r1 squared. For the point mass, that one's easy. It's just mr squared, but this for the point mass or clay, so m2 r2 squared. There you go. Now we can substitute, right, knowing we have to add omega to state the angular momentum. So angular momentum of the cylinder, that'll be 1/2 mass 1. I don't have to add initial because the mass is not changing. And then radius 1 squared. The radius is not changing either, right? The turntable is not getting any smaller or bigger. Times omega initial, right? It has a some initial speed, which we know here. That should be equal to now 1/2 m1 r1 squared, because the radius did not change, nor did the mass, times the final velocity, angular velocity, plus now angular momentum of the point mass. That would be m2 r2 squared. Again, the mass of the clay is not changing, nor is its radius, times omega final. We have to solve for final velocity. We can factor out, right, this omega final here. And if you're thinking you can cancel this term, 1/2 m1 r1 squared, with this one, you can, because we have different omegas. So let's factor this out. So this side stays the same for now. m1 r1 squared times omega initial will be equal to, let's factor out the omega final, parentheses, 1/2 m1 r1 squared plus, I don't need the omega because it's outside the parentheses, m2 r2, and that's it. Now all we have to do is solve for omega final. Whatever this is, it's going to be a number eventually, so do treat it as such. So let's just divide by this whole thing, this right here. That'll be, I'm just going to write it again once, okay? And then I'm going to copy. So m1 r1 squared plus m2 r2 squared. Whatever you do to one side, you should do it to the other. I'm going to copy. There you go. Man, I need to move this a little bit, right? It's too cramped. Alright guys, give me just a second to fix this. There you go. Now I will move this one. Oh no. That's fine, I can fix it. Let's move this over here, and there you go. I'll fix this. I know it looks off-center, but I'll fix it. And this whole thing cancels. So now we have that. I'm going to write it over here. we have that omega final is equal to 1/2 m1 r1 squared times omega initial. This is the left side, the original left side. Now I'm going to copy again this side of my equation, okay, here, divided by this. Now, if you were to substitute numbers now, you would get the correct answer provided you are very careful about it. I'm going to simplify it a little bit. I know this 1/2, I can write it as 1 here and then 2 here, right? This 1/2. And if I do that, this 2, the 2 will cancel this half. And then I'm going to have to add a 2, right? Because I'm distributing the 2 here and to m2 r2 squared. Therefore, a slightly cleaner version would be m1 r1 squared divided by m1 r1 squared plus 2 m2 r2 squared. What I did is I had this 1/2, I put it like this, so this cancels this one, 2 to 1/2, and then I had to place the 2 here. Okay, that's what I did. And from here, you can find the answer. It's very simple. You just substitute your numbers and, well, let's do that, right? Why not? Why not? So, final omega would be m1, 17 kilograms, times r1 squared, 2.9 meters squared, times omega initial, 11 radians per second. We're going to divide all of this. I changed color. Let me go back to purple. All of this to, we'll divide it by, I'm sorry, that would be 17 kilograms again, m1 r1 squared, 2.9 meters squared, plus 2 times m2, which would be 4 kilograms, times 0.91 meters squared. There you go. This, I'm using this one over here, okay? Now let's see if I can use decimals. Let's see. So we had, let's do door parentheses. So M1, that was 17 kilograms. I think so. Times R1 squared, 2.9. Uh-oh. 2.9, there you go, squared times 11. You're going to divide that by 17 times 2.9 squared plus 2 times 4 times 0.91 squared. And there you go, 10.51. I said nearest hundredth, so 10.51 it is. That is our angular velocity. Let's go back to one note. So the final velocity would be 10.51 radians per second. All right, and that's it. This is how you solve it.